Okay, thank you so much, and thanks so much for having us here. This has been a great day so far. We've had a chance to meet a lot of professors and tour around the facilities. We love talking to educational institutions and students and faculty because you guys are the people that are inspired to think differently and to see challenges differently. I think we, yeah, need a little bit. Okay. Oh, a little bit. Everything we're going to be talking about today can be powered on the power of a cordless drill. So that is, we're talking about a motor about this big, and yet on this much power we can achieve human flight and we can break highway speed limits. The projects here are really about doing more with less and looking at things from a different perspective and really looking at unconventional solutions. So we got our start in 2006. We started on the Human-Powered Ornithopter project. And the goal here was to achieve an ancient aeronautic dream, to fly under our own power in the imitation of a bird. This is something that people have dreamed about for hundreds, if not thousands of years, looking up at a bird and saying, I want to do that. And really we thought, after all this time, we were finally in a position where something like this was actually physically possible. And we jumped at the chance to try it. So just first of all, a lot of these aircraft, a lot of these vehicles are a little bit difficult to describe kind of in scale and just their magnitude. So we'll start it off with just a short introductory video. So when we got our start in 2006, we had a reasonable background in flapping wing flight. Both Cameron and I were grad students under Professor Delorier, who had specialized in flapping wing flight for about 20 years before that. But what we knew absolutely nothing about was actually how to build a human-powered aircraft. And as we go through our story here, just share a few little tidbits of kind of what we learned along the way. In order to work outside the box, we must understand what's inside the box. And for everyone here, I mean, you start a new research project, the first thing is the lit review. And it's very important to not try to reinvent the wheel. So we started out with an epic road trip. We went across basically went across the entire eastern United States, visited every single human-powered aircraft in the eastern United States. It took about 4 days. There's really not too many human-powered aircraft. Yeah, I mean, what we learned is really to be able to feel it and touch it and see it. If you want to be the best at something, if you want to truly understand something, you really have to meet the best people in the world and talk to them face to face. And actually, I don't know if you can see very well, but that's actually Professor Forbes right there. He's just joined your faculty. I'll actually transition this mic.
So in trying to come up to speed on the state of the art in human-powered aircraft, we first looked to aviation visionary Paul MacCready, who in 1977 had built the Gossamer Albatross that crossed the English Channel. This propeller-driven aircraft was successful where none before had been, despite 50 years of trying. And his insight was to build it both incredibly light and incredibly large, and thus sufficiently low-powered for its very meager human engine. When we built the Snowbird some 30 years later, it was 105 feet in span and weighed only 95 pounds. So this was the size of a commercial aircraft, but weighs less than some of the oversized luggage. The entire thing was built a lot more like a model airplane than a regular airplane, and it was extremely fragile, and we had to be very careful with flight testing this incredibly delicate aircraft. Most of the structure was built from carbon fiber tubes, which is, yes, state-of-the-art aerospace material, but the rest of it is balsa wood and foam and plastic film. It's really not like anything you've ever seen before. So we had this airplane. It was different than most before. Most had propellers. So with flapping wings, we basically have to get all the thrust from the wings, and this is pretty straightforward to do. You just have to design the wings such that throughout the flapping cycle, the average thrust is in the forward direction. So now that you know what you need to do, how do you do it? We focused on a very simple approach. The pilot simply pulls down on the wings, and the natural elastic tailoring of the wing gives you the twisting profile that you need throughout the flapping wing stroke. So we didn't have either any active methods or any hinges or anything like that. It was very simple and very straightforward. But where it was mechanically simple, it means that the engineering design process was very complicated and very involved. And this is where all of the complexity of making this airplane comes in. We decided when we were doing this to use multidisciplinary optimization, which we knew from Professor Martin's class is a very powerful tool. It's also useful because the design of this airplane was going to be non-intuitive. There's a lot at play. There's the aerodynamics, the structures, and also the human model, and getting everything to play together in exactly the right way to design and build an aircraft that's right on the edge of success requires a pretty cutting-edge strategy. So I'll go through each of the models that we put together for this analysis and then how we made it run. It's important to remember when we're putting this together that this is kind of the foundation that we laid for the work that made the helicopter possible. Without the knowledge and the, say, first kick at the can that this design process represented, we might not have had the ability to satisfy the next impossible goal that we went for. The aerodynamic model was basically focused on computational simplicity. We wanted something to run very quickly on a laptop, but even so, we wanted to capture what you can see, the unsteady wake that results from these flapping wing motions. So this was a simple model that one of the undergraduates on our team programmed, and it was well correlated with some of the other higher fidelity models we had, as well as experimental data. So it was basically just good enough to capture what we wanted without having to be run on supercomputers. The structural model was not only, say, a very simple finite element model to solve for the wing deformations, but a lot of the time that we spent went into the failure analysis and the accurate characterization of each of the structures. We're basically trying to build the entire airplane so that it will all break at the same time. There's a very low factor of safety everywhere, and so we basically tested hundreds of specimens to figure out how close could we get to failure everywhere. And we kept chasing failure modes until we ended up seeing weird like pop can buckling stuff, some more typical composite failure modes here. But basically we had an entire airplane that we were comfortable was on the edge of failure, but thankfully not quite there. So the third model that I mentioned is the human model. We basically have an airplane that, because it's a large flapping wing design, it's not very efficient. So versus the power requirement of most other human-powered aircraft, it's actually substantially higher. So we really have to do better. Furthermore, Todd is a fantastic human engine, but he's best when he's pedaling his legs. With the kind of rowing motion that we used for the Snowbird, it takes quite a knockdown to the power that you can produce. So it's almost a 25 or 30% hit. So again, we really have to make sure that we get everything we can out of the power plant. So here we did a bunch of testing to basically see when does our engine fail at different power levels. And what we did, for example, in this simple trade-off, we were looking at flapping frequency. And so this is the power of the aircraft versus frequency. And this is basically the blood lactate level in Todd at various various stroke frequencies. And you can see that the minimum flight frequency and the minimum blood lactate don't really coincide. So this is a good example of a difficult trade-off that we had to make. Fortunately, the difference between the optimum here and up here for flight power is not substantial. It's maybe 10%. Whereas it's physically impossible for the human to output the kind of power required at this lower frequency. So this was a point where we said, okay, if Todd's legs will break at this frequency, I guess we have to operate in here. So this was a good example of the kind of thing where we did some empirical tests, we had a model, we had to make a trade-off, and that ends up being part of the whole design. So we have all of our models that work together, and we mainly were using the aerodynamic and the structural model in an iterative solver that alternates between them to come up with a solution. It's doing this many times for every analysis of a candidate airplane design. That being said, it's not as if it works every time. Our design approach was fairly halting at this stage. It required a lot of babysitting and a lot of hand work, but the framework was there, our sense of working with an optimization scheme were there, and it was something that was usable, and it certainly allowed us to do more than had we been, say, looking at the aerodynamics and the structures completely separately. Once we have the solver working together, we basically wrap that in an optimizer, which is a code that it very quickly seeks the ideal solution given your models. So for example, there's the analogy here of a ball trying to roll downhill. This map here kind of represents your design space. And what the gradient-based solver does is looks for the path of least resistance to minimize, in this case, the power required to fly the airplane. So this is what we end up with, the Snowbird. It's very light, it's different than most other aircraft. You need ladders and a farm tractor to assemble it, but overall it is, I don't know, a really interesting looking aircraft and really fantastic to fly, albeit it's a lot of early mornings to minimize your wind exposure. So we succeeded with this airplane in August of 2010. We sustained flight for about 20 seconds and 160 meters, which is longer than the Wright brothers flight. So naysayers. In any case, this had basically achieved our project goal and the ancient aeronautical dream that was our target. So shortly thereafter, we were struck by another itch. The Atlas Human-Powered Helicopter was inspired by the Sikorsky Prize. In 1980, the American Helicopter Society put up a prize for the first human-powered helicopter to fly to an altitude of 3 meters and sustain flight for 60 seconds. This prize had been around for a while, and a lot of people had tried, but really nobody had put the whole package together. Really, no one was even close at the time that we had started. We saw University of Maryland trying, and we said, maybe this could be something really fun to get back into. Maybe this is something that we could create a career doing, kind of seeking all of the most impossible and exciting challenges that were out there. So we really had to go at it and jumped in with both feet, and that was the start of this project.
So in case you're wondering, no, those videos are not in slow motion. The rotor RPM is about 10. So yes, these are a very interesting aircraft. So as Cam said, there had been other teams that had been trying before we got into it. And of course, we started our background research by looking at these teams. Cal Poly had lifted off the ground for about 7 seconds with a helicopter that it has propellers on the tips that drive the rotor blades. The Yuri in Japan had hit 19 seconds with a quad rotor, and at the time the University of Maryland had hit 11 seconds also with a quad rotor. But what was interesting, with these designs, to reach 20 seconds and a couple inches off the ground compared to reaching 3 meters really was going to require an increase of efficiency of almost 3-fold. So we're talking, at this point, no one is really anywhere close. So we're looking at this thinking, there's a lot that we can learn from this, but something is going to require a very drastic change. Interestingly, one of our first ideas was to look at a hinged rotor system. For anyone interested or knowledgeable about helicopter dynamics, the beautiful thing about a helicopter is that you have a hinge at the root, you spin the blade fast enough, and the centrifugal forces keep the blade down while the lift forces are trying to push it up, and you have zero bending moment along here. You can build an incredibly lightweight blade. And so we're thinking, okay, we're going to make a 20-meter long blade. We're going to spin it really fast, and this thing's going to be a piece of cake. So, of course, we start setting up some fairly simple aerodynamic simulations and start kind of optimizing this and having a look at the situation. It turns out that as your rotor radius goes up, your coning angle, beta, really starts to go up. And this is assuming we're throwing 5-kilogram weights on the tip, which for a human-powered aircraft is kind of like sticking an anvil on the end of your wing. But it's, so we're spinning around, this to get a reasonable coning angle. You're talking about spinning a blade that's maybe an inch or two in chord, that's 50 to 50 feet long. So it's not totally impossible, but it's maybe a little bit impractical. So we started on a design study looking at every possible configuration that we could think of, including these hinged rotors. So this is a plot of the required power versus the altitude, going from 0 to 3 meters. And of course, at low altitude, we're in heavy ground effect, so we're benefiting from that. The hinged solutions are up top. This is kind of a reasonable range of what's physically possible with a male pilot of 175 pounds. The hinged solutions are, definitely way too high. This here is a typical configuration, a tail rotor and a standard single rotor. May be possible, but definitely not as good as these 3 configurations. So it's really interesting. Sometimes in configuration studies, you end up with totally different designs that all kind of require about the same amount of power. So this is looking at a counter-rotating design, a quad rotor, and a design where you drive the propellers drive the rotors with a propeller. So we dropped the counter-rotating design, knowing that something this large, with any small changes in angle of attack, there is a good chance of kind of colliding blades. We didn't know. This was not a problem that someone had solved before, whereas the quad rotor and the prop-driven design people had flown with at least. So we focused in on basically an aerostructural optimization of both of these designs, trying to fully optimize each of these designs before deciding exactly what we were going to build. So having the experience of having built, built these models and gone with gradient-based optimization before, we kind of knew what we were looking for. And we're looking for aerodynamic and structural models that give us very smooth output. We don't want something that with small changes in the input, you're going to get some noise in your output, because then the gradient-based optimizer gets stuck. So we're looking for something that works very quickly, because we need to use this for design. We want to navigate a huge design space. We want to optimize this design, and we're also looking for something that's very smooth. So our structural model, now we've got tons of validation. We've built a lot of carbon fiber tubes. We have very good models that have empirical validation. And what we're really focusing on here this time around is an improved aerodynamic model. So the aerodynamic model is actually inspired from by what some people have done in bat flight. This is actually quite a while back, where you assume that one, you can neglect all the complexities and assume that in one stroke the bat is going to shed a vortex ring. And they keep on shedding these vortex rings, and you can then model this and see how these rings interact. So we definitely took a step further, a little bit more complex than this, but basically what we're doing is taking the helical wake and flattening it out into a series of kind of planar wakes. And then we're running a free wake solution to let this wake basically do what it would actually do. So the helicopter and hover is actually a very, very complex problem. We're looking for a steady state solution. So we want to know, we're just sitting here in hover, we're not moving anywhere. But what you need to do to calculate that is actually run a free wake model where you're letting the wake curl up on itself, and this can be very computationally expensive. So we simplified it to using symmetry. This is pure hover. We simplify it to a 2D model, and we're using an inverse design method. So we prescribe the lift distribution, and then we are computing what the wake is doing and what the downwash is. And then we'll figure out afterwards exactly what angle of attack we need to achieve that lift distribution. And using these methods, we're able to greatly simplify the analytical model and have a code that literally runs in under 2 seconds on a regular desktop computer. Also looking at, in the end, we're looking for stability in these models. We're looking for smooth outputs. And there's a lot of details that we've kind of put into the code, things like a vortex core model. So if two of these little vortices get too close to each other and the induced velocity becomes very high, it doesn't go shooting off to infinity, and then we get a jagged solution. So there's things like that we were thinking of from the beginning in order to get a smooth function so that we can use optimization. And of course, we have to validate this model. A lot of what we're looking at is whether or not this model can capture the benefit of ground effect. So we're operating in deep ground effect. This is the altitude as a function of how many rotor radiuses you are above the ground. And this is the required power versus over the required power if you were at infinity, completely out of ground effect. And you can see at about 1 rotor radius, you're maybe 90% out of ground effect. So anyway, we're operating in this region here, and this is what we want to be able to capture with this model. So now we've got a very fast aerodynamic code, and the thing that we did with the structural model here as well, if you have, it really is a combined aerostructural problem. You want your rotor tips to be as close to the ground as possible. If your wing is very flexible, once you start spinning them up, they're going to bend a lot. If your tip is losing the benefit of ground effect, it's going to require more power. So you'll put more weight into the spar to stiffen it up, or in our case, we had bracing lines underneath as well. So we prescribe the lift distribution. Now the beauty of this model is that, again, it's an inverse design code. We prescribe the lift distribution, which means we don't have to iterate between our aerodynamic and structural model. So we prescribe our lift distribution. With a structural model, we compute the deformations. And then with our aerodynamic model, we get the required power. And of course, we have a whole bunch of other design variables. We can adjust the chord length, the spar geometry, where the bracing wires are, what kind of airfoils we have. And our structural model is also spitting out the, how close everything is to fail. We have a composite laminate failure model. We know when all the laminates are going to fail. We know, what the failure is looking like along the whole spar. And we have a very accurate estimate of the total weight. So this now sets us up for a very efficient gradient-based optimization scheme. We have our design variables. We have our constraints. We say we don't want it to be above 70% failed. We don't, and we know that lift has to equal weight. And then, of course, our objective function is minimizing power. That's what we're trying to accomplish. So what you end up with is highly optimized rotor. And this is really cool. In human-powered aircraft, or I mean, typical helicopters, you don't really see blades like this, but this is the aerostructural optimum, and really it looks more like an optimized wind turbine blade. You've got a nonlinear taper, we have a tapered spar, and custom airfoils along the section. So now we can go back and answer the two most important questions. What kind of aircraft are we going to design? Is it going to be a quadrotor or a prop-driven design? And how big does this thing have to be? Which is very, very important to all of this. So again, very interesting. We've fully optimized two designs, and it turns out that a quadrotor and a prop-driven design are almost identical, to within error of our, of our assumptions. The interesting thing here, so we ended up going with a quadrotor for a variety of other reasons. But partially it was because, or a main reason was, we had seen a prop-driven helicopter fly for 7 seconds, quite unstable, wobbling about. We've also seen a quadrotor helicopter fly for 20 seconds, very stable. So we know, we went into this, we didn't want to take too many risks. Really our goal was to go in, spend 4 months on design, 3 months on construction and build, and then win the prize within a total span of 8 months. So I know it's fairly ambitious. We didn't quite nail it in that time period, but really we didn't want to take any big risks in saying, maybe a prop-driven is a tiny bit better, but it's going to take us 10 years of research. So we went with a quadrotor. And now the second big question is, how big is this thing going to have to be? Turns out that everything in this range down here is roughly twice the size of anything that's ever been built. And I think one of the big things that allowed us to achieve this was the ability to free ourselves from unnecessary constraints. Every helicopter that had come before us had constrained themselves to fly inside a gym, because that's both convenient and available, but also it seems kind of reasonable. The size seems a little bit more reasonable. We definitely went to something of somewhat an unreasonable size. The actuator disc area of the Atlas is twice as big as anything that had been built before. And actually the actuator disc area is just about the same as if you add up the actuator disc area of every helicopter that had flown before. So we're going very, very big, and with that, of course, there are many associated problems or risks.
So one of the biggest risks of building a helicopter this large is that we didn't know what we didn't know. There was a chance that it would be extremely large and flexible. With human-powered aircraft, again, incredibly light and incredibly large, that doesn't really bring to mind a stiff structure. So in addition to the fact that we might have something that looks like a wet noodle in flight, we have to figure out how to make it light. And again, this thing is 160 feet across. It's about the size of, say, a 777. So we need to think about substantially different and more creative solutions absolutely everywhere to get this thing within the realm of possibility. So the first and biggest single item we had to look at was the overall structure, the truss. And so here we said, okay, some people have done cantilevered booms. What we wanted to do is actually turn this into the most efficient structure we could think of, which was an arch. So though it looks like these trusses are cantilevered, in fact, we have all of these bracing lines underneath and around the helicopter that turn it into a much more efficient arch structure. So this means that we can make something that is much larger and much lighter, and it's still reasonable, and we can hopefully get the stiffness in it that we need. That being said, when you sit on the bike at the center, you sink 1 foot. So it's a little bit eerie to get on and you immediately think, oh, I'm breaking it. But fortunately, that's not the case. Designing this was really interesting. The flexibility that we would get meant that the way that it would behave in flight was non-intuitive. But we used, again, optimization to make sure that we were getting the best we could out of the materials, and that, given what we wanted from it, which was the rotors need to be this far apart, it was as good as it could be. We used A really interesting way of doing this, we used carbon fiber tubes for all of the compression members, and then the rest of it was actually made with pre-tensioned string. This was, again, the lightest and most innovative way we could think of to do this. All the string, as I say, was pre-tensioned at all times, probably to like an E flat or something like that. We spent a lot of time twanging things and making sure that they were all at the right tension so that everything was twisted in all the right ways. The other thing that was really interesting that fortunately there was precedent for before was the drive system. So you're not going to use belt drive or chain drive. The lightest way that people had done this before was like a reel-to-reel tape, where basically you start at the rotor hub with a very thin line. It's only like 2 millimeters. It's like a very overglorified fishing line, wrapped up around the spool, and then it comes to the center of the bike and wraps up around the small spools here. So as you're pedaling, you are unwinding from the rotors, winding it onto the bike, and at the end of a minute, you run out of string, so you better be back on the ground. In order to get, say, the gear ratio that we wanted, again, bearing in mind how fast our human engine could spin their legs, we had to come up with some really, interesting and bizarre stuff. So the rotor spools, for example, looked more like modern art than pieces of a flying machine. We basically took inspiration from a bike wheel, which was way different than most people have done in this area before. And in fact, each of these rotor hubs takes about 1 kilometer of yarn to make, and a lot of student hours. But this was a great example because we started with a solution that seemed like way out in left field, but was kind of the most perfect way that we could think of to build this, a bicycle wheel. It was super light, and we basically broke it and fixed it and broke it and chased down all the failure modes until we had something that could bear 150 pounds of torque, but only weighed 1 pound. So it was really an unbelievable solution. The key message here is start with what you think is the absolute pursuit of perfection and work your way backwards until it's practical. So we had designed and built Atlas in this barn in about 4 months. We had an 8-student team, and it was a really exciting atmosphere. We were all super driven. But once we had built it, we spent 8 months flight testing. There was so much involved here. We basically had to contend with weather and with unbelievably fine adjustments. The helicopter, 160 feet across, requires pitch adjustments in the rotors on the order of 1,000th of an inch. So it was really quite a dichotomy. It was also really interesting because, again, it's a commercial aircraft. They usually operate out of hangars, for example. We had to break ours down into a truck, assemble it 2 hours at the beginning of every morning, break it down 2 hours at the end of every day. It really was a bit of a crippling constraint, but again, we're making a human-powered aircraft. There are a lot of weird constraints and things that we have to operate with. But that being said, this was, an interesting and somewhat difficult time, as you'll see.
So as Cam mentioned, flight testing was definitely difficult. We came in with the goal of, as I said, design 4 months, build 3 months, fly for 2 weeks and win this thing. Ended up being about 9 months of flight testing. And really began to sink in that, failure is really a necessary part of success when you're trying to do something that's never been done. And I mean, everyone here, you guys are all trying to do something that's never been done. And it's a really cool environment. But there's a lot of failure involved. We really began to appreciate this over many structural failures. We had a lot of tip strikes. I think we broke a total of 18 rotors. We only had 8 of them. And twice, we were literally within inches of success, and the whole thing came down on top of us. So really, I think what we learned on this is that you design something and you build something, and at that point, I think you're about halfway there, like literally halfway there. There's so many things that you don't know until you actually go fly it. And one of the really cool examples was the control system. So one of the things that I think there's no way we could have predicted this before we built the helicopter. We had such a cool control system at the beginning. You're sitting on the bike and you've got these control handles that you pull on, and then there's hundreds of feet of wire that are going up through the truss, down to the rotor hub, through basically like a kind of 1 degree of freedom swash plate, and then all the way out to the tips. And then you've got little canards on the front of the tips that when you actuate them, they actually twist the blade. So you change the lift distribution of the blade, and now we get a nice clean, increase in lift. So you take this rotor, you increase its lift, you take this rotor and you decrease its lift. That gives you control, and you drift wonderfully in the direction that you had intended. We had a lot of problems with the control. The flexibility of the structure wreaked havoc on everything. Any imbalance in the control actuation forces would send blades out of whack, and we'd be breaking spars against the ground. And what we ended up realizing when we finally got things working enough that we could actually see what the controls were doing, we found that when you went to power up this rotor, what was actually happening was you power up this rotor, the driveline force to that rotor is going to increase. And that increase in driveline force actually bent the whole structure, tilting the rotors in the wrong direction. So for the first few seconds, you'd actuate the controls and you start flying in the wrong direction. And then this would eventually climb higher than this rotor, and then you'd start flying in the right direction after about 8 seconds. Meanwhile, after 8 seconds, you've probably crashed into a wall if someone wasn't holding on to you. So, we're like, oh wow, like this, there's already been enough problems with this, but I think that, an 8-second controlled delay is probably something that you can't really work with, especially if there's control reversal to begin with. And but what we realized in seeing that was how we could take advantage of that flexibility. And so what we ended up doing was attaching 4 really thin control lines that go to the bottom of each rotor hub, and then they connect to the bottom of the bike. And when you lean, what you're actually doing is pulling on that line and flexing the structure. So you bend the whole structure and you get thrust vectoring. And for something this size, the response time was incredibly fast. You lean, and within half a second to a second, your aircraft is traveling in the direction that you want it to. We shed about 8 pounds off the helicopter. We got rid of the winglets. We saved a lot on drag. In the end, this control system weighed about 100 grams and could control instantly. It was intuitive. You just said, I think I want to go that way, and there you go. This is something that I don't think we really could have envisioned if we hadn't spent so much time testing and so much time crashing. So that was really cool. So back to the crash, or one of 2 crashes. The last time we gave this talk, this is sort of where we ended. We said, we just crashed, but we're going to rebuild it, and we'll be back. And then we were back, and we crashed again, and then we were giving another talk, and we said, we just crashed, we're rebuilding it, and we'll be back. So anyway, I'm very happy to say that we did rebuild it, we did come back, and on June 13th, we blasted through 3 meters and managed to capture this prize, which had remained untouched for 33 years. So that was our adventures with our human-powered helicopter.
So we've done the impossible twice. What do we do now? Over the past few years, we've been working, while we were students at the University of Toronto, on what we call speed bikes. These are the fastest vehicles we've ever worked on. They are powered solely by the human, capable of highway speeds. This bike just 6 weeks ago did 125 kilometers per hour on level road. So yeah, this is faster than I drive in my car unless I want a speeding ticket. So the incredible thing about these is that they show that if we prioritize aerodynamics and efficiency, what we can do. And these lessons are especially transferable for, say, automotive technology and whatever the next solutions are in personal transport. The drag of this bike is 1/10 that of even the best car on the market. I mean, if you look at it in direct comparison, you get 1,600 equivalent miles per gallon versus an average of 27. Like, it is mind-blowing and completely out of the park. It really shows what we can do if we think differently. And that's really what our goal is going forward, is, as we said, inspiring people to take on the impossible, think differently, and really evaluate what our current solutions are for our most pressing problems and figure out better answers. This is really, we are trying to inspire people to enter the pursuit of perfection. We're doing this with a lot of the strategies that you're looking at in your aerospace department. We have advanced CFD that we're going to start using. We use extended runs of laminar flow. They're really all technologies that are transferable to cars if people were willing to take a good look at it. The most exciting thing about this field as a whole is that it is of unlimited potential. This is basically what a UCI legal bike like your Tour de France bicycle has set in an hour over, say, the entire past century. It's pretty much been solid at about 45 kilometers an hour. People aren't really going much faster. But this is speed bikes, the kind of bikes that we're interested in working at, and it's going like a rocket. Just again, a few weeks ago, a student team from the Netherlands broke the human-powered land speed record at 133 kilometers per hour. So next year, what we're hoping to do is go back and break 140. So this is our focus. The reason that people are able to do these incredible things with bikes is because the community is extremely passionate about what they're doing. It's much like the academic community, and their passion drives the creativity to do better and make strides and improve the efficiency of these bikes. Every year we go to the World Human-Powered Speed Challenge, where people come from Russia, Netherlands, France, the UK, US, Canada. Everybody brings the best in land vehicle aerodynamics and really shows what they're made of. And it's this open community that's really driving continuous and incremental improvements, and that will really push the land speed record to 140, 150. Who knows what the limit is, and who would put a number on it? That would be silly. This is a taste of things to come. Thanks very much for having us.